Thank you, thank you. So yeah, I'm going to explain what this word salad means firstly. I'll say that the word almost is used a little bit sarcastically, in that you still need to be able to use a lead proof assistant to do this. So it's actually, it requires quite a bit of knowledge, but you'll see once it's running that at least there aren't too many lines of code required to verify this. So anyway, we'll see how that goes. But yeah, so the Zirgen MLIR is, Nethermind has been collaborating with RISC to try and to formally verify their implementation. And we'll talk about this a bit in a second, but essentially they have this language called the Zirgen MLIR, which is some intermediate representation for zero-knowledge circuits. And we've developed some tooling to formally verify that, but we'll get into a bit more detail. So first, I'll give a little bit of background on of general ZK background. So firstly, I imagine most people in the crowd will be familiar, but essentially a zero-knowledge protocol is a two-party protocol that has a prover and a verifier, and the goal of the protocol is to prove that is for the verifier to convince is for the prover to convince the verifier that it knows the answer to some shared problem without necessarily revealing what that problem is, what the solution is even. And ZK, so one traditional way of expressing this problem, which the prover and the verifier share, is what we call a ZK circuit. So a ZK circuit is just a system of multivariate polynomial equations over some finite field, right? And so as we mentioned, these can be used for expressing all sorts of things, including, as we said, with RISC zeros, it's a ZK VM that executes RISC-V programs, I should say. But it can be used to express all sorts of domain-specific problems, like a hash function, etc. And then there are things like Cairo, RISC-0, pi squared, that can use it for all sorts of to express all sorts of general-purpose computations and expressing the execution of general-purpose programs, Turing-complete programs, right? And so, as I mentioned earlier, right, so the Zirgen MLIR is this DSL for expressing these ZK circuits, and there are a bunch of others, Halo 2, Circom, etc. And actually, at the same time as I'm giving this talk right now, we also have a Halo 2 extractor, which Ilya, my colleague, is talking about in the other room. But unfortunately they clashed. It's a little bit unfortunate. But here I'm going to talk a little bit about as I said, our form verification tool that we've developed for the Zirgen MLIR. So, you can't really see that very well. So yeah, I'm going to start off by showing you a little bit of an example of the Zirgen MLIR, but we'll do a relatively quick flyover. So this is, you can see, thank you, yes. Oh, no, yes, that's better. That's better. So so you can see this is a fairly simple piece of code, but it might look like quite a lot actually. But this is a snippet of Zirgen MLIR. So by the way, MLIR is a LLVM construct that stands for the multi-level intermediate representation, and it's It's a parameterizable intermediate representation that can be used to essentially tailored to express the semantics of a bunch of different things, including, it turns out, ZK circuits, right? So here's this simple simple snippet of the Zirgen MLIR. This function is called is0. It does exactly what you'd think. It takes some input, and it gives you an output that tells you whether the input was 0 or not, right? So it gives you it outputs a 1 if the input was 0, and it outputs a 0 otherwise for all other inputs, right? So the first thing I'll tell you about the semantics of this language is that it has 3 types, right? So the first thing is we have what we call a field element, right? So that's just some element from this finite field that we use in our system of multivariate polynomial equations. We also have buffers. Buffers are essentially arrays of statically known length that contain these field elements, right? And they often act as, we have input and output buffers, which are essentially the values that the input values and output values of your circuit, right? And so essentially we receive both of these as inputs, and we constrain these values inside of this code. And the third type that we have is actually a constraint, which is essentially a system of polynomial equations on these values, on the input and output values, right? Fairly straightforward for the moment. So yeah, okay, we've got a bunch of things. It's fairly, the first command just assigns, you can see a bunch of assignments, right? And essentially after each command, I've written what the state update that corresponds to the line before is, right? So the first one is really straightforward. We assign the constant 1, which is in the field, right, to the variable called %0. True is actually the constraint true, so it's satisfied by any single assignment of the inputs and the outputs. We then have these get commands which essentially fetch elements from a buffer. So the first command fetches the 0th element of the input buffer, which we're going to call in. The second command fetches also the 0th element of the output buffer, which we're going to call out. Also, well, in a second I'll explain yes, I forgot to mention. So you can see the fixed lengths in the type, right? So arg0 in the arguments to this function has, in the buffer you can see that it's of length 1, and arg1, which is the output buffer, is of length 2, right? So yeah, and as I said, well, given what I told you the semantics of is 0 is, why do we have 2 outputs? Well, we'll get there in a second, right? Okay, so we've got these get commands, and then I'll just quickly go through the semantics of the next 2 commands, and we'll just skip to the end. So the next 2 commands are constructors that allow us to construct from one constraint to more constraints, right? So essentially what it does is it takes a constraint and a value, and it constructs a constraint that is equivalent to the original value. So you can see this on the line underneath. So we say P and, that little wedge symbol for those who aren't logicians, means and V, the second value inputted, is equal to 0, right? So P, as we know, is true here, because that's %1 in the argument, right? And the second argument that we have is %2, which we know is in. And so essentially this constraint boils down to saying in is equal to 0, right? And so we're building up, keep in mind that we're not asserting that this is true, we're just constructing a constraint, right? And we'll return, the constraint that we return at the end, right, with this return 11, is actually the constraint this is actually the constructed circuit, essentially, right? Okay, so you know what AND-EQZ means, and you know, and cond is a conditional conjunction, right, which takes a constraint, a value, and another constraint, and essentially it gives you, as we can see here in the line underneath, that the constraint is true, and if the value given is not equal to 0, I don't know if you can see the not equal to 0, this implies that the second constraint must hold, essentially, right? And so here the arguments we have are %1, which is true, right? So that's kind of boring. The value that we have is our output value, and the constraint that we have is a constraint we just constructed right before, which is in is equal to 0. So all of this says that, well, if out is not equal to 0, we know that in is equal to 0. And you can see we're starting to build up the semantics of the circuit that we actually want, because we know certainly that if the output value is not 0, in this case we'll want it to be 1, but we'll check that later, we certainly want the input to be 0. Right, make sense? Perfect. Okay, so now there are a couple of other commands you haven't seen. The only commands actually you haven't seen here are sub and mul, and they do exactly what you think they do, multiplication and subtraction inside of the finite field, right? But let's skip all the way to the end, and we return this constraint 11, which you can see is this construction here. And let's reason about it a tiny bit. So if the input is equal to 0, we say, we're going to need a tiny bit of information about the theory of finite fields here, which is every element inside of a finite field has what we call a multiplicative inverse, apart from 0, right? So every element has another element of the field that you can multiply it by to get the number 1, essentially, right? And so if in is 0, we know that, well, in times out 2 here, right, is certainly equal to 0, and minus 1 is not equal to 0, and so the consequence of this implication is false, and so consequently the antecedent, so 1 minus out 1 is not equal to 0, must also be false, and so then we know out 1 is equal to 1, right? Similarly on the other, and then similarly if in is if in is if in is not equal to 0 on the left hand side, we know that, well, the antecedent of that implication is also false, and so once again out 1 must not be equal to 0, i.e. out 1 is equal to 0, and that's how we build these constraints here, right? But reasoning about this by hand is pretty tough, and so we want to try and automate this as much as possible. And so we're going I'm going to show you in a second a methodology for doing this. To construct this tool, we've used a proof assistant that is called Lean4, and I'm going to tell you a tiny bit about that very quickly now. Actually, how am I doing time-wise for here, just to judge?
You have 10 minutes.
About 10 minutes, okay. I'm going to skip part of my demo in that case. So I was meant to give a quick demo of how to use Lean here, but we're not going to do that, actually, because it's going to take too much time. But yeah, I'll tell you a little bit about Lean4. It's what we call an interactive, firstly it's a programming language, but it's also what we call an interactive theorem proof. An interactive theorem proof is just a programming language that has such an expressive type system that I can express statements in higher order logic into its type system, essentially, right, at a very high level. And this means that essentially I'm able to express, arbitrary theorems about things that I want to verify in types, and then I'm actually able to prove these things in the language, right? And so all of this is done via what we call a dependent type theory, and I'll just skip over this really quickly. So to give you an idea, because a lot of you that will just sound like magic to you, how is all of this done? But to give you a high level idea, well, you guys, I'm imagining most people in this audience are familiar with programming languages. So you'll be familiar with in programming languages having this dichotomy between terms and types, right? So you have your terms or statements in your language, which you can compose in various ways, as this arrow represents, to build larger, more complex programs, right? You can nest statements in oh, hey Tanishq. Sorry, I didn't see that. So you can nest statements in if branches, in while loops, etc., right? And that's fairly typical. Some languages will also allow types to refer to themselves. You can have type constructors, like some languages will have vectors, which are parameterized by other types, and you can construct a vector of ints or chars or whatever you want, right? Some languages also allow terms to depend on types. So you can have, and we call this polymorphism, right? Where you have some term in your programming language which, depending on the type of the thing passed to it, it might take different kinds of numbers like a float or an int. The notion of addition or multiplication will be different, right? And so the semantics of the program will depend on the type of the thing passed in. And then finally, and this is where the magic happens, in dependent type theory, you also allow the types to refer to terms. So in your types, you can actually refer to the functions you defined in your program, etc. And this allows you to essentially express within your types theorems about your programming language and about the semantics, right? Okay, and in particular, so Lean is pretty interesting in that it's a very modern proof assistant, right? I think it's learned a lot from its ancestors, so to speak. It has a very powerful notation engine, so the parser of Lean is basically arbitrarily reprogrammable. And I think that's pretty cool because essentially, all of my mathematician friends, I can get theorems to be basically expressed in exactly the notation a mathematician would use on paper, right? And so I can just show this to them, and they immediately know, they might not understand the proof, but they immediately know what it means, right? Okay, and the other thing is that there's a huge corpus of formalized mathematics in Lean, which we call MATLAB, in particular field theory, which we've been talking about quite a lot, right? So that's great. Okay, perfect. So the problems so in practice, actually, when trying to automatically generate specifications for programs written in the Zirgen MLIR, sorry, my mouth is super dry. Apologies, guys. We noticed a bunch of problems with trying to automatically generate specifications for them, which was that actually when actually considering their semantics, it would quickly be the case that the state updates that we were modeling via these state transformers became out of control. They were so big that essentially Lean's type checker would experience a buffer overflow, which was not great, right? And so we had to apply a bunch of optimizations to actually simplify the code while preserving the semantics in a way that would allow us to actually be able to construct these terms and construct these specs, right? So the first thing that we did is we chunked the code, we cut it up into smaller parts. We then computed state transformers for each one of them, and then obviously composed these to actually get a specification for the whole piece of code, right? So if you basically get a spec for the first chunk here, the second and the third, and then compose these, you get a spec for the whole thing, right? The second thing that we did is that we found that actually a huge amount of the intermediate representation of the state when we were trying to compute these state these state transformers in Lean was taken up by a lot of variables that were actually not used anymore. Right, so a lot of variables in this program at some point in time, they're never going to be used again. They just disappear, but they still had to be dragged along in the state, right? But you can forget them without actually modifying the final value which is returned here, right? So we then added the option of inserting these drops, which basically told the language model that, hey, this variable is not going to be used anymore. Right, and so you can just throw it away. And we automatically generated a proof at the same time using these shuffling lemmas that actually this program is semantically equivalent to the original program before the chunking and the drops were inserted, right? And that proof is completely automatically generated. We say that the evaluation of this program, thank you so much. Sorry, 4 minutes, okay, perfect. The evaluation of this program is equivalent to the original, right? So yeah, after applying these optimizations, we found that actually we were able to verify some fairly large programs in the Zirgen MLIR, including some programs that were about 300-400 lines of code, which is fairly good, I thought at least. So obviously there's still some scaling required to get it to be practical, but yeah, we'll see how that goes. We're still working with them. Okay, perfect. So I've got 4 minutes. I think actually I'm going to have to skip the demo, yeah, basically. But I'm going to tell you a little bit at a high level about how this actually works in practice, generating these specs, which is essentially, I talked a little bit about, well, we model the programs with these state transformers, right? So how do we actually automatically generate these state transformers? So one way would be to, hey, write a program that automatically tries to go through these lines of code and sequence all of these state transformers. But actually that turned out to be pretty tough. What we did in practice was actually we formalized the Zirgen MLIR and Lean. We gave it a formal semantics, right? And then what we did is we wrote what we call a VC, a verification condition generator, which all that it does is it just writes a proof that of a simplification of the Zirgen MLIR. So it takes a program, it traverses it, goes through it line by line, unfolds the semantics of each line, applies some simplification tactics that exist in Lean already, right? And that automatically just generates a simplified specification for this. So what we do is we generate this proof that just unfolds and simplifies within Lean. We chuck it at Lean. We ask it, hey, what's the type of this thing, right? And it throws us back a type, which actually happens to be a specification. It's a state transformer, a simplified state transformer that actually describes which describes the semantics of the program that was given to us, right? Very straightforwardly. Okay, so I think I've got like, what, 2 minutes left?
I think so.
About that, okay. So what I'm gonna do very quickly is put this microphone down and actually show you guys a spec that was generated here. We'll go, and then we'll go on to the last slide. Perfect, 1 second.
I will allow it.
Thank you, you'll allow 2 minutes over, okay. You're generous. And of course, since I already had another demo, I need to pull this one up because only the first one was up. It will take only a second though. You're timing me, are you?
No.
Where is it? There we go. Okay, perfect.
If you need a few more minutes, it's fine, by the way.
Thanks. Okay. There we go. Is this for the constraints? Yes, it is. Perfect. So, okay, perfect. Let me see if I do this. It should appear here, and ooh, that's a bit messy on something this size. Yeah, okay, that's a bit better, hopefully. Perfect. So this is actually a specification. It's still not, let me make it a bit smaller.
Can Control K and then Z?
Now it can be seen, right? And this is actually a specification for this the circuit that you saw earlier, the is0 circuit. This is a specification which is automatically generated for it, right? And in fact, you'll see in Lean, well, I'll show you very quickly in Lean afterwards that it's actually been formally verified. And so this is an auto-generated specification which says, okay, so data 0 is the output value, and we say, hey, if it's if it's not 0, then the input must have been 0. And the other one says, well, if 1 minus data 0 is not 0, because the true branch is kind of not interesting,
If it's not 0, then, so i.e. data 0 is 1, essentially, right? Wait, if it's not 0, no, so data 0 is 0, sorry, then we know that this must be true, essentially, which is saying that, hey, the product of in 0 and data 1 is equal to 1, essentially, right? And so that must mean that essentially in 0, as we said from our background in field theory, is non-zero, essentially, right? And so this was automatically generated, and from this we're able to verify all of this up to now is automatically generated, the extractions, the optimizations, the specification, and it's in fact proved in Lean. So if we look very quickly check our goals, hopefully, if we go right here at the end, we'll see that we have no goals. So that means that Lean is happy that this is actually a proof of this statement. So we formally verified it end to end. Okay, perfect. And then actually from this we can very straightforwardly prove the more human readable spec that we had. Perfect, okay. Let me go back very quickly now to the last slide, which is somewhere. No. There we go, perfect. Last slide. So yeah, I wanted to talk very quickly about some limitations and some future work we need to do. So the first thing, the easy ones, is that it actually doesn't support all of the operations in the Zirgen MLIR. There were some slightly spicier ones that we didn't quite get to, but we're working on that. And then obviously modularity, we need to be able to split up these proofs and split up the circuits into sub-circuits and reason about them individually to make it easier for humans to do this. I realize I haven't been holding the microphone. Anyways, hopefully that's been that can be heard. Okay, it'll be fine. And then obviously the performance, it takes actually, I wasn't able to run the demo, but it took a solid for 3-4 minutes to do a fairly simple circuit, but we're still working on improving the performance. And finally, the ongoing work here is that we actually want to prove that the constraints used by RISC 0 are actually equivalent to the RISC 5 spec. So yeah, we'll see how that goes. Thanks so much, guys. A bit bumpy, but hey, we've got that. Cheers.